Okay, so now let's consider how we can develop a log linear model for this tagging problem. So in general, we'll assume that we have some input sentence, W1 through Wn. For example, this might be something like the dog barks. And I'll sometimes use the following notation. I'll use W sub 1 colon n to refer to this entire sequence. Okay, so wi is the ith word in the particular sentence. And in addition, we have some tag sequence, t1 through tn. So we might, for example, have the sequence dnv equal to t1 through tn. And similarly, I'll use this notation t sub 1 colon n as shorthand for this entire sequence. Now, the key idea in log linear models is we'll see how to construct a model of the conditional probability of any tag sequence given an underlying word sequence. So there are going to be many possible tag sequences for our given input sentence. So let's say, for example, we have, many other possible tag sequences. I'm running a few of them down here, and so on and so on. We are going to assign each of these tag sequences a probability. So we might have 0.1, 0.2, 0.01, 0.001, 0.005, and so on. And if we sum up all these probabilities, they will sum to 1. Okay, so we have a well-defined conditional distribution over the set of possible tag sequences for this particular input sentence. Now, one very important thing to realize is that this is in quite stark contrast to the case we saw for hidden Markov models, for HMMs. So remember, in hidden Markov models, we actually defined a joint probability distribution over tag sequences paired with word sequences. Okay, so first interesting thing to see in these log linear models is that we will directly model this conditional distribution, and we won't actually attempt to model this joint distribution here. So that's the first key difference from hidden Markov models. Once we've derived a model of this particular form, we can then apply it to a new test sentence. So if I have some test sentence W1 through Wn, then I can take the most likely tag sequence, T star, to be the tag sequence T1 through n that maximizes this conditional probability. And remember, with HMMs we had something very similar. In fact, we would have T star 1 to n is equal to argmax T1 to n of the joint probability of T1 to n and W1 to n. So it's really very similar, except again we're using a conditional probability here for the log linear case, whereas before for the hidden Markov model we had the joint probability. So there are going to be some key questions we'll answer in this lecture. Firstly, how do we define this conditional distribution? How do we estimate the parameters of the model which underlies this definition? And then finally, we'll have to answer the question, how do we actually efficiently find this most likely tag sequence for a given input sentence? So the critical question is going to be, how do we model this conditional distribution, the probability of a given tag sequence T1 through Tn given a particular word sequence W1 through Wn? And again, we'll see this method used where we first use the chain rule, and secondly we use independence assumptions which simplify the model. So here is a first application of the chain rule. So I'm going to write this probability as a product of terms. So I have one term for each position, j equals 1 to n, and then I have the conditional probability of the jth tag value conditioned on the full sequence of words W1 through Wn, and in addition conditioned on the previous j-1 tags. This step is, as usual with the chain rule, it's exact in that any distribution, any conditional distribution of tags given words can be decomposed into a product of terms in this way. So that's step one. The second step is to make an independence assumption, which actually looks very similar to the Markov independence assumptions seen in our trigram language models and then in our trigram HMMs. So what have I done here? I've basically replaced this sequence of tags T1 through Tj-1 with just the last two tags in that sequence, Tj-2 and Tj-1. And I've just been a little careful here to make sure to define T0 and T-1 to be our special star symbol, which is basically the symbol at the start of the sentence. So what I'm saying here is that each tag informally only depends on the previous two tags. More formally, it means that the value for this random variable tj is conditionally independent of all the tags preceding the previous two tags once I condition on the entire sentence and also the previous two tags. So again, this looks very much like the Markov assumptions we'd seen earlier in the class. The only real difference is that we're conditioning on the entire sentence throughout this decomposition. So we're carrying along this entire sentence. Here again is the independence assumption that's made in this model. So let me give you a particular example. Say I want to write down the conditional probability of the tag sequence DNV given the three words the dog barks. Then this is going to be decomposed into a product of three terms. So firstly, the probability of D, given that I have the sentence the dog barks, and given that the previous two tags were star star, which were our start symbols. So our sequence essentially looks like this. We have star star D and V. We're going to have one probability term for each of these three tags. So the second term is going to be P of n, given the dog barks and star D. And the third term is going to be P of V, given the dog barks and dn. Okay, so again, each tag has a probability term, P of tj, that's conditioned on the previous two tags and in the entire input sentence. The critical question now is going to be, how do I estimate these probabilities? How can I define a model for these probabilities and estimate the parameters of that model from training examples? And we'll see that this is going to be a direct application of the ideas from log linear models that you saw in the lectures in the last week of this class.